So this video is about learning what this thing called power series is. So, at this point, you've probably already learned what a regular series is. And a regular series is something of this form, a sub n, where we're adding up an infinite amount of numbers. You take a sequence and you add up all the terms, and if it converges, we say that it equals a number, and if it diverges, then it is basically plus or minus infinity. And so, we have a whole bunch of tests to test for this convergence, and it's kind of been a huge focus in the class so far. But now we're going to tackle this thing, which is called power series. And if you were looking at the intuition that we brought up with this whole study of sequences and series before, a power series will look very familiar. So a power series is something that looks of this particular form. So we're going to start at 0 this time, and it has a sub n times x to the n. And what this looks like, if I were to write out some terms, if I plug in n is 0, I'm just going to get kind of the 0th term here, and then I'm going to get a sub 1 times x to the first power, and then a sub 2 x to the second, plus dot, dot, dot. And what you end up getting here is a really, really long, an infinitely long polynomial in terms of the variable x. So this power series consists of two parts. It consists of a sub n, which, is basically, a sub n is a sequence on its own, but, in this context, it is a sequence whose terms are basically the coefficients in this polynomial. And then x to the n, of course, manifests itself as these x's, x to the 0, x to the first, x to the second, and so on and so forth, that we would find in any polynomial. Maybe some will be missing, maybe some won't. And so maybe just like an example power series that you might see. So maybe as an example power series you might see might look something like, well, just this basic power series from n equals 0 to infinity, where our coefficient, our little a sub n sequence here is just a sub n is basically just equal to 1 the entire time. So maybe instead of writing those brackets, just a sub n here is equal to 1. And the terms in this series is just going to be, well, if I plug in 0, I just get 1. So I get 1, and then plus x, and then plus x squared, and then plus x cubed, and dot, dot, dot. Now, again, earlier on in the class, I've provided kind of some intuition for why we were studying sequences and series. And so I'm going to go back to revisit that concept really quick with our good old friend Desmos. So here is a function, y equals 1 over 1 minus x. And, in Calculus 1, this is a trip down memory lane. We learn how to come up with these things called tangent lines. And we can make tangent lines at any point, but I'm just going to make one right here at x equals 0. So at the point, maybe I'll put this in, at the point 0, 1, on our red graph of 1 over 1 minus x, I can create a tangent line. And the tangent line is a reasonable approximation of the values of the red function, 1 over 1 minus x. It's a reasonable, attempt at approximating those y values as long as we stay kind of what we call close to x equals 0. So if we go too far, right, and let me just take a screenshot here and illustrate this. If I stay maybe kind of within these x values here, it kind of looks like any y value that I would pick that lies on the green line is reasonably close to the actual y value that would exist if we were to plug in an x value into the red function itself. But if we go too far away, right, if I start picking x values from over here, then the y value of this tangent line does not match the y value of the red graph very, very well. And so the idea is, a tangent line is a good approximation, but we can make this approximation better. And we don't learn about this in Calculus 1, but we're learning about it in this class if I add on another term, if I make, say, a quadratic. And you might notice now, right, let's take this screenshot, that now the range of values for x that I could maybe pick from is like a little bit further, right? Maybe kind of like from here to here, the approximation is even better than the tangent line one was. And you know, the big idea behind all this is that if I keep going, if I were to add another term, right, and I start making this polynomial longer, the idea is that, you know, how many terms would I need to add until I get a perfect approximation of this red graph? And the answer is something that I brought up in the intuition was the more terms that I add, right, the better it gets. So in theory, we have an idea that maybe if I add infinitely many terms, then this polynomial would approximate the value of this red function 1 over 1 minus x, and it would do a really good job of it. And so that's kind of like our idea. That is our motivation for studying power series. So this particular power series right here is just, you know, a power series is basically just an infinitely long polynomial whose coefficients, you know, might change. Now, in regular series, right, with a regular series, we say that a regular series will converge if when you add up all the terms, you get a number, right? That's what it means. So what do you think, you know, using the context of what we just did on Desmos, what do you think it means if a power series converges, right? If I say if a power series converges, right, what does that mean? Well, what it means, right, it means, right, what does a power series converge to? Does it converge to a number? Does it converge to a donut? Like, what does it mean? And a power series will converge to a function, right? That's the idea. You add up all these polynomial values, and it turns out that, again, courtesy of Desmos, that we have an idea that we can start maybe, you know, matching these other more complicated functions. So if a power series converges, that means it means that the power series equals some function, right? I'm going to underline that, some function. Okay, now there's a caveat to this, and I'm being kind of loose with the definition right now, but just to kind of, you know, toss it out there, you know, maybe just to give you all another example. Another example is this power series, which is 1 over n factorial times x to the n. So again, here's our little a sub n, right? That's all of our coefficients. So if I write out some of these terms, if I plug in 0, the first term here is going to be 1. If I plug in 1, the next term is going to be x. But then I start getting 1 over 2 factorial, which is just 1/2 times x squared. And then I get a 1 over 3 factorial, and that's 1/6 x cubed plus ... And it turns out that if I keep this pattern going, we haven't shown this so far at all, but if I keep this pattern going, it turns out this ends up equaling the function e to the x. And so the idea is that, you know, I can approximate values of this function y equals e to the x with this really infinitely long polynomial. And it turns out that, you know, depending on where we're doing this approximation at, you know, like in Calc 1, we learned that using just the first two terms, what we called a linear approximation, or the tangent line, is a good approximation of e to the x as long as we're kind of close to where we made the tangent line. That was the idea that I just went over in Desmos. And we could add on some terms, and a quadratic is a little bit better, and a cubic is a little bit better. And the idea is well, maybe, you know, I don't need this infinitely long polynomial to work with. Maybe, you know, if I had to consider plugging in x is equal to 100, well, I don't know how to do this without a calculator, but I could definitely plug in x is 100 into this, at least like the first four terms here, right, the cubic, and I could, you know, approximate the answer with like a little bit of algebra. Now, is it close enough? Well, depends on your definition of close, and a couple other things. But that's the idea, right? The idea is that it may turn out that we have some really nasty functions like natural log of secant of e to the tangent of x or something like this that we really don't want to be working with. We don't want to talk about taking the derivative of this or the integral or even evaluating it at values of x. But if I told you that I could approximate it with a polynomial that looks like 1 plus x over 3 plus x squared over 5 plus x cubed over 7, like maybe there's some, infinitely long polynomial that I, have shown mathematically is the same thing as this function, then you can start asking questions. Well, like what is the value of this when x is equal to 2? You can just choose to plug it into this polynomial. And then, how many terms do you want to plug it into? Well, kind of depends on how much error you want in your guess. There's mathematical ways of showing that, but that's not really the focus of what we're doing right now. The focus is just to get our feet wet with this notion of a power series as this infinitely long polynomial. And so, it will be in our interest to determine whether or not a power series will converge, because that may not be something that crossed your mind. We just said, well, if a power series converges, it converges to a function. But when we talk about convergence, that's kind of a weird thing when we start talking about things like polynomials. But let me just toss an idea your way. What if I were to plug in the value, because this is a polynomial, so I can plug things in for x. So what if I were to plug in x is equal to 2? What would I get, right? I claimed that this thing was equal to 1 over 1 minus x. If I plug in 2 into this, right, I get -1. But there's no way that I'm going to get -1 if I plug in 2 in here, right? I get 1 plus 2 plus 4 plus 8, right? I'm going to get infinity. We're adding up a bunch of numbers that keep getting bigger and bigger. There's no way that I get -1. And so then the next question is, okay, well, did you just lie to us? You just said that this power series, this infinitely long polynomial, adds up to equal 1 over 1 minus x. And heck, you were on Desmos over here showing us, you started adding terms and you said it got better and better and better. And I said, yeah, that's true, but you might notice that it's not working for all of 1 over 1 minus x. In fact, where it turns out that this approximation is only good for values of x between -1 and 1. And I guess I shouldn't put a bracket because technically falls apart there. Between -1 and +1. It turns out that the approximation is really good as long as we choose x values in that region. And of course, to address the fact that as we get closer to the ends over here, the approximation starts to kind of get worse, we would need to add on more terms to our infinitely long power series. But the theory is that if I were able to add infinitely many terms, this green function, this representation of our power series, would perfectly essentially approximate the values of this red graph between -1 and 1. And then afterwards, it might still just skyrocket like that or just tank completely like that. So, the natural follow-up is, okay, well, clearly, right, we have an idea that if this power series converges, it would converge to a function. And Dylan told us that it's going to converge to this function. But at the same time, I also just brought up the case that this case doesn't work for every single x value, right? I claim that it's going to converge. And so let's examine that claim just a little bit. So if we look at this series, right, x to the n, and then we're going to start from n equals 0 to infinity. Now, before I write this down, I just want to point out, a lot of people say, well, Dylan, your series is starting at 0, and all the other ones we did started at 1 or 2 or 3. Can we start at 0? Yeah, like an infinite series, right, is adding up infinitely many terms. It doesn't matter if I start counting from 0, 1, 2, or 3. The reason why we have that is because the general formula for a power series is a sub n x to the n. And typically when we write this out, that gives us a constant, a linear term, and a sub 1 times x, a linear term. It gives us a quadratic term, et cetera, et cetera. And so starting at 0 allows us to just have notation that basically fits the form of something that we're very familiar with, right? A line is y equals mx plus b. We're used to having that form, so that it just kind of matches that. But back to this this series x to the n. Now, this series, if I write it out again, so we get 1 plus x squared plus x cubed plus dot, dot, dot. If we look really closely, or if you had someone like me to point it out, you might notice that this is actually kind of geometric in nature, right? Every single one of these terms is being multiplied by what? Well, it's being multiplied by x, right? And you're like, okay, so what? Big deal. Well, we have a convergence test for that, right? Actually, in fact, we could figure out what this thing adds up to, right? If I say that my common ratio here is the variable x, we have a test that says if this thing converges, it's going to converge to a over 1 minus r. We have a formula for an infinite geometric series that satisfies a certain condition about r, but just putting that off to the side for a sec, this a in that formula represented the first term in the series, so that's 1, and then our r here I'm claiming is x. It's the common ratio going from term to term to term. So on the one hand, this is geometric, and so you're like, okay, so it does add up to 1 over 1 minus x. But this condition only holds if what is true about our common ratio, right? What is true about r? Well, it has to be true that the absolute value of r is less than 1, or in other words, that r is between the values of -1 and 1, right? That our common ratio has to be such that all of the terms are getting smaller and smaller and smaller and smaller and eventually approaching 0. So inherently, that tells us that this convergence holds, right? We do add up to equal this function. This power series will add up to equal this function if, and only if, I'll say will work only for values of x, between -1 and 1, or you could say the absolute value of x less than 1. And that was, again, very apparent in the Desmos picture, where we saw that this approximation really looked good between -1 and 1, but after that, it kind of goes haywire and stops being a very good approximation. So now that we kind of have this idea very, very loosely that, okay, we have a power series. Power series has coefficients, right? Every power series has these coefficients, right? So the one I showed you for e to the x, which I haven't proven yet, has this little sequence right here. That's our coefficients. It starts with 1, then it's a 1 again, but then it's 1 over 2 factorial, 1 over 3 factorial, so on and so forth, and that gives you e to the x. And then these coefficients over here, the coefficients is just a sequence 1, right, repeating. So we get 1, and the coefficient here is 1, and 1, and 1, and so on and so forth, and that gives us 1 over 1 minus x. And so, it's, if you're paying very close attention, you might notice that all of these series, they also, every single one has an x squared, an x cubed. This one has an x, this has an x squared, has an x cubed, etc. So the only thing that's really controlling what function we converge to is what? Well, if they all have x squared, x cubes, the only thing that's really that is in control of the function that we're going to converge to are these coefficients. So the idea being that somehow, if we know what those coefficients are, right, if we have a formula for them, that somehow that formula, that little sequence a sub n, dictates exactly which function this is going to hopefully converge to. So that's a little nugget to kind of keep in the back of your mind. But more importantly, what a lot of people want to know about is how do we test for convergence of a power series? So how do we test for convergence of a power series? Right, we just did one, and because it just happened to be geometric in nature. But what about, for instance, what if we do a power series n equals 0 to infinity of Let's see, what should we do? N to the third over 3 to the n times x to the n. Okay, what if we do something like this? So here's a power series. You could write out some terms if you want. And so if we plug in n is 0, I'm going to get 0 for the first term. So plugging in n is 1, I'm going to get 1/3 times x, so 1/3 x. If I plug in 2, I'm going to get 8 over 9 times x squared. And then, we could keep going, so on and so forth. This, again, is just going to be some infinitely long polynomial. And the question is, does this converge? Yes or no? If it does, it's going to equal some function. Now, just like with all of our other series that we ever worked with, we had all these convergence tests, and a lot of time we just did the convergence test, whether it was the alternating series test, the integral test, comparison test, whatever it was. We would just say, yes, it converges, but we never knew how to add up all those terms to be like, all right, what number does it converge to, right? We did this test. We said it converges. What number does it converge to? We didn't know the answer. The only one we know the answer for is a geometric series. And at least for right now, we're going to say that's the same thing. Right now, we are not able to figure out what function this is going to add up to, right? I don't have any idea looking at this, right? This clearly, right, whatever function it adds up to is really going to be dependent on what these coefficients end up being. But even looking at this, like, I couldn't tell you what this ends up equaling, right? We saw that e to the x had a bunch of coefficients that came from factorials, and I just kind of pulled that out of thin air. So we're not interested in what does it converge to. Right now, we're just interested in does it converge. And it turns out that luckily for us, we can use the same exact convergence test that we already know and love. And specifically for power series, the ratio test is going to be our best friend. The ratio test, is Chuck Norris's favorite test. On the 8th day, God made the ratio test. This is going to be our good friend for solving these power series convergence questions. So we can just run it through the ratio test, right? Let's do it. And so we do limit and approaches infinity. We're going to compare the terms and make sure that they're getting smaller over time. And so we're going to look at the n plus 1 term. So n plus 1 cubed over 3 to the n plus 1. Then we have an x to the n plus 1. And then the denominator, we're just going to have n cubed over 3 to the n. And then we have x to the n. And so we run it through the ringer. So we limit as n approaches infinity. We make sure we're very careful with our algebra here. So let's write things where they belong. So we have an n plus 1 cubed and x to the n plus 1. Now in the bottom, dividing by a fraction is the same thing as multiplying by the reciprocal. So we'll get 3 to the n up here. And then we should have 3 to the n plus 1. And then left over n cubed times x to the n. So at this point, hopefully we haven't made any mistakes in our algebra. And now we do a little housekeeping. So x to the n plus 1 and x to the n will cancel and just leave us with an x on top. The 3 to the n and the 3 to the n plus 1 will cancel and just leave us with a 3 on the bottom. And again, if you ever have trouble doing this, I just say plug in your favorite number for n, right? So if you're not sure why 3 to the n over 3 to the n plus 1 simplifies to 3, plug in like 4 for n. What's 3 to the 4th over 3 to the n plus 1 would be 5. 3 to the 4th over 3 to the 5 becomes 1 over 3. So 3 to the n over 3 to the n plus 1 just becomes 3 in the denominator as well. And then the n plus 1 cubed and the n cubed we can't cancel. So we have now just limit as n approaches infinity. We have the absolute value of n plus 1 cubed times x over n cubed, right? And at this point, we make an observation that should not be too hard, but it's that this x term has nothing to do with n, right? We're taking a limit as n approaches infinity. And so what that means is we are afforded the luxury of being able to just take it out. So we can remove this x, we'll leave it in its absolute value, but we can kind of factor it out, if you will. And then we have limit n approaches infinity, n plus 1 cubed over n cubed. And that limit very quickly is just 1. So this is the absolute value of x. And what do we know that needs to be true about the ratio test? Well, the ratio test only works if whatever the answer we get for the limit ends up being less than 1. Now, we do need to test if it equals 1 because that is that is what we call an inconclusive result. But we're definitely going to be guaranteed that whatever this power series is will converge for if we pick x values less than 1. So turns out that it does equal some function, and it's going to equal that function at the very least for the x values between -1 and 1, not including the endpoints. But since this is inconclusive for when this thing equals 1, right? It's inconclusive for that. We're going to test when the absolute value of x equals 1. So that means we're going to test the endpoints. And we're going to do this because, again, the ratio test is inconclusive when our result equals 1. And so what does this mean to test our endpoints? Well, when does the absolute value of x equal 1? Well, that's going to happen when x is equal to 1, or it's going to happen when x is equal to -1. So let's take a look at what happens to our series if we choose x equals 1. Right? So if we choose x equals 1, this series n equals 0 to infinity just becomes n cubed over 3 to the n. Now, we could do a little bit of finessing here, and you would have to go and show whether or not this thing converges or diverges. Because I'm lazy, I'm going to go ahead and say this thing does converge, the intuition being that an exponential is incredibly larger than n cubed, and so this thing will end up converging, but you would need to do another one of the tests that is appropriate for this series to show whether or not this converges. But the idea is that if this converges, right, if this converges, then it turns out that x equals 1 will also work for our power series. And likewise for x equals -1, if we plug that in, we're going to get n cubed over 3 to the n with -1 to the n, which makes this an alternating series. And that one is actually really easy to test whether it converges because 3 to the n is growing so much faster than n cubed. We can show that this is decreasing and has a limit of 0, and that's enough to satisfy the alternating series test. So if it converges for both of these, then we would say that the end result here is that our series n equals 0 to infinity of n cubed, right, our power series, this long, infinitely long polynomial will converge. We'll say converges. What does it converge to? Some function. What x values will it work for? It will converge for all x values for x in this little range of -1 to 1, any x value in that. Or you could say absolute value of x less than or equal to 1 or whatever you want. Okay, so that's power series kind of in a very brief nutshell with just one example. They do get slightly more complicated as you go, but this is kind of the general idea. Power series is just an infinitely long polynomial. If it converges to a function. The idea of a power series is that working with a polynomial or some terms of a polynomial is much nicer than working with some really nasty function. I guess one thing that I want to point out is that this definition of the power series is going to need a little bit of clarification, and I'm going to modify that definition really quick and write something down here. X minus, we'll say, what do I want to say? I'll just call it A. This is kind of bad notation, but they usually say centered at A. And then n equals 0 to infinity. So this is the definition, the form of a power series. This is a power series, what we call centered at x is equal to a. And so what this might look like might be that you have a power series like n equals 0 to infinity of, 1 over n factorial times x minus 3 to the n. And I claim that this is still right? This is still the approximation for e to the x. It's still the power series for e to the x, but it's what we call centered. It's centered at x is equal to 3. And what that means, roughly speaking, I'll just do a small sketch of kind of what this means. In the example we did for 1 over 1 minus x, when I drew the tangent line was drawn like this, right at the point 0, 1. And then if I did the quadratic, right, the parabola was kind of centered at still the point x is equal to 0, y is equal to 1. It was centered at x equals 0. And then when we did the cubic, right, the cubic ended up being something like this. And still, it was kind of like centered at x is equal to 0. And so the idea is that if I want to approximate e to the x, but I want to do it for the points around x is equal to 3, what this would do is it would take the graph for e to the x, which looks something like this. We'll say this is just e to the x. And instead of starting to make our tangent line approximations here, right, at x is equal to 0 or stuff, it's going to start making them at x is equal to 3. And it ends up like starting there. And so what that means is if you write out some of these terms and you let n equals 0, right, n equals 1 is going to give you x minus 3. N is equal to 2 gives you 1/2 x minus 3 squared, etc. The idea is that if you say, well, I only want to use the first couple of terms to approximate the values of e to the x, you can just use the first couple terms. But if you choose to like try x is equal to -7, if you pick some value for x here, odds are that your approximation that's given by this polynomial is not going to be very good, because x is equal to -7 is really far away from x is equal to 3. We'd probably need to add a lot more terms to this polynomial before we could start picking points at x is equal to -7. But if I were to try to plug in the point x is equal to 3.1, I'd probably have a much better chance of being correct, because this power series is what we call centered at x is equal to 3. So it's going to be the most accurate if we pick x values that are quote unquote close to x is equal to 3. Now, what is close? What's acceptable? What's not? There's a whole study of this that involves error and what percentage away is acceptable, what percentage of error is fine, and you can actually generate the intervals, like how far you can go in either direction, that kind of fit within your error parameters. But I'm going to stop there. This is, I think, a good enough kind of solid introduction to what power series are and the general idea. And the next video is going to be on something that I mentioned before, which was we noticed that in all of these power series, no matter what kind we worked with, there's always x to some power, right? There's always this pattern of x's, x squared, x cubed, x to the fourth. There are power series where they don't exist, but more or less every single power series starts in this form. So the only thing that changes are these coefficients a to the n. And we said that, somehow in these coefficients, not a to the n, this is a sub n. Somehow in these coefficients is encoded what function we are going to converge to if we do converge to. So the next video basically covers, well, how do we get these coefficients, right? Can we figure out a way? Is there a mathematical way to come up with these coefficients that will then make this entire power series converge to some function? Or in other words, can you give me a function, right? Can you give me a function and tell me a way to generate this power series? Just like in Calculus 1, I can give you y is equal to x squared, and you can create a tangent line equation, what we call a linear approximation, y equals mx plus b, where the slope of our tangent line is given by the derivative located at some point that we're interested in coming up with the slope at. So that's the idea. That's kind of where we're headed. And if you're interested in that, let's head on over to the next video.